Welcome back to Very Ordinary Differential Equations. In this lecture, having discussed the Laplace transform, we now discuss the inverse Laplace transform. So remember, if you have a function f of t, the Laplace transform is given by capital F, sometimes written L of f, where capital F of s is the improper integral from 0 to infinity of e to the minus st f of t dt. When capital L of f is capital F, we can also write that little f is L inverse of capital F and say that it is an inverse Laplace transform of capital F. In other words, if capital F is the Laplace transform of little f, then little f is an inverse Laplace transform of capital F. Rather than directly derive inverse Laplace transforms of arbitrary functions, we're just going to use known Laplace transforms, combine it with linearity and the shifting theorem to work out inverses. As a first example, let's find an inverse Laplace transform of capital F of s, which is equal to 6s squared plus 2s plus 1 over s cubed plus s. Whenever we have a rational function, and they're going to come up a lot, and we want to find an inverse Laplace transform, we're always going to do it with partial fraction decomposition. We're only going to give the details of partial fraction decomposition in this one example. We presume that you've done partial fraction decomposition before, and you've mastered it. If you haven't, practice it, because you're going to need to do it a lot in using Laplace transforms and inverse Laplace transforms. So we factor the denominator into linear and irreducible quadratic terms. That's easy enough. It's just s times s squared plus 1. Since s squared plus 1 has no real roots, that cannot be factored further. So then, we're going to presume that our function capital F of s can be written as something over the linear term s plus something else over the irreducible quadratic s squared plus 1. Since our original function has a lower degree on top than it does on bottom, so should each of these pieces. This is a first degree polynomial, so its numerator should be a 0 degree polynomial. This is a second degree polynomial, so its numerator should be a first degree polynomial. So we want to find the constants a, b, and c, so that a over s plus bs plus c over s squared plus 1 is indeed equal to capital F of s. So we are assuming that capital F of s can be expressed as a over s plus bs plus c over s squared plus 1. Now when I find a common denominator of these two terms, it's just s times s squared plus 1. So a must be multiplied by s squared plus 1, and bs plus c must be multiplied by s, and then I am adding the two together. So how many s squareds do I have? I have a times s squared, but I'll also have bs times s. So that's a bs squared. So overall I have a plus b s squared. How many s's do I have? Only c times s. And how many constants do I have? Just this a times 1. So when we give these a common denominator and combine, we end up with a plus b s squared plus cs plus a all over s cubed plus s. But remember, this is supposed to be capital F of s as given in the problem. So a plus b, being the coefficient of s squared, should be 6, because that was what the coefficient of s squared was in the numerator of capital F. Also, the numerator of s should be 2, so c should be 2, and this constant term should be 1. So we find capital A is 1, capital C is 2, but also a plus b must be 6. Therefore, since we already knew that a is 1, if a plus b is 6, b must be 5. So we can now write capital F of s is a over s, 1 over s, plus bs plus c over s squared plus 1, 5s plus 2 over s squared plus 1. So now what we're going to do is look in a table of Laplace transforms for similar functions. Here's what we found for capital F of s. Instead of writing it as 6s squared plus 2s plus 1 over s cubed plus 3, we've applied partial fraction decomposition to write it as 1 over s plus 5s plus 2 over s squared plus 1. In any table of Laplace transforms, you would find the following. If little f of t is a, then capital F of s, its Laplace transform, is a over s. The Laplace transform of a sine of omega t is omega over s squared plus omega squared, and the Laplace transform of cosine omega t is s over s squared plus omega squared. So here we have a 1 over s that very clearly matches this. 5s plus 2 over s squared plus 1, however, we're going to have to tackle differently. Specifically, we break it up as 5 times s over s squared plus 1 plus 2 times 1 over s squared plus 1. 5s plus 2, 5s plus 2. So now we have 1 over s, 5 times s over s squared plus 1, and 2 times 1 over s squared plus 1. Each of these matches these three terms here. So since the Laplace transform is linear, so is the inverse Laplace transform. Therefore, I can take an inverse of all of this. Since it's linear, I can find an inverse Laplace transform of 1 over s, 5 times an inverse Laplace transform of s over s squared plus 1, and 2 times an inverse Laplace transform of 1 over s squared plus 1. Here, if a is 1, 1 over s has inverse Laplace transform 1. If omega is 1, then here we actually have s over s squared plus 1, s over s squared plus 1. So the inverse Laplace transform with omega equals 1 would be cosine of t. And in our last term, 1 over s squared plus 1, that matches omega being 1. 1 over s squared plus 1 squared. So its Laplace, inverse Laplace transform would be sine of t. So overall, 1 plus 5 cosine of t plus 2 sine of t is a function whose Laplace transform is the capital F we began with. In other words, this is an inverse Laplace transform of capital F. As a second example, find an inverse Laplace transform of capital F of s, which is s minus 1 over s squared plus 4s plus 3. The denominator factors directly as s plus 3, s plus 1. Partial fraction decomposition of capital F of s would then allow us to write this as 2 over s plus 3 minus 1 over s plus 1. I wasn't lying when I said the previous example was the only time we were going to show the details of partial fraction decomposition. So work through it yourself and verify that indeed partial fraction decomposition of capital F of s will yield this, 2 over s plus 3 minus 1 over s plus 1. From any table of Laplace transforms, you would find the following, that the Laplace transform of e to the at is 1 over s minus a. So each of these matches that form. This is s minus negative 1, s minus negative 3. So therefore, since inverse Laplace transform is linear, I can take an inverse Laplace transform of this, factor a 2 out of here, giving me 2 times an inverse Laplace transform of 1 over s plus 3 minus an inverse Laplace transform of 1 over s plus 1. The first is just going to be e to the minus 3t, and the second is just e to the minus t. As found in any table of Laplace transforms, you'll find this entry right here. So here we have 1 over s minus negative 3, 1 over s minus negative 3. Therefore, this is the Laplace transform of e to the minus 3t. There we have it. And similarly here. So now we have found a function whose Laplace transform is capital F of s. As our third and final example, find an inverse Laplace transform of 1 plus 2s over 9s squared plus 6s plus 3. The denominator is actually already an irreducible quadratic. It has no real roots, so there's no partial fraction decomposition that we can reasonably accomplish here. Now, if we look in a table of Laplace transforms to find which capital F of s have irreducible quadratics in the denominator, there are actually a few. So, the Laplace transform of sine, cosine, e to the at times a sine, or e to the at times a cosine, all have irreducible quadratics down in the denominator. We need to know which one we're dealing with. The second row, however, is just the shift theorem applied to the first. If I already knew the Laplace transform of sine, if I multiply it by an exponential, by the shifting theorem, its Laplace transform will be a shifted version of the Laplace transform we already found. Similarly, if I know the Laplace transform of cosine, then e to the at times cosine will have a Laplace transform that is a shifted version of the one we already found. So this second row is just a shift version of the first. Now what we need to do is manipulate our denominator to either be in the form s squared plus omega squared or s minus a squared plus omega squared. Those were the denominators we found in our table of Laplace transforms. So first let's factor out the 9. 9s squared plus 6s plus 3. If I factor out the 9, it leaves behind s squared plus 2/3 s plus 1/3. Completing the square in there gives me s plus 1/3 squared plus 2/9. Okay, so overall our denominator, once I factor out that 9, can be written in this form here, s minus negative 1/3 squared plus something squared, giving me 2/9. So once we factor the 1/9 out, we know which form we're looking for. So here is our function with that 1/9 factored out. So we've identified that we want our denominator to be in the form s minus a squared plus omega squared. Well then, a had better be negative 1/3, and omega is the square root of 2 divided by 3. This makes our denominator here s minus negative 1/3 squared plus root 2/3 squared. Now from the previous table of Laplace transforms, we need our numerator to either be omega, root 2/3, or s. So we're going to split this function capital F into two pieces. All right, so here's how we have capital F represented at this point. Now we want to break it up into two terms. However, one term should have numerator omega, which is root 2/3, and the other should have numerator s minus a, in other words, s plus 1/3. Let's deal with that second part of getting a numerator of s plus 1/3 first. So 2s is what we have up there. Now that's 2 times s plus 1/3 if I then cancel out the 2/3 introduced by subtracting it. So 2s is now going to be represented as 2 times the quantity s plus 1/3 minus 2/3. So now here is our function capital F of s. Now in the numerator, notice we have a 1 and a minus 2/3. Simplifying that, we just get a 1/3. Here is our 2 times s plus 1/3. We still have this 1/9 hanging out in the front. Now inside, I can break this up into two pieces. The 1/9 has been factored out. Here's my 1/3 over the denominator plus 2 times s plus 1/3 over the denominator. This bit here, I can now handle pretty nicely. I've got s minus a over s minus a squared plus omega squared. I can take an inverse Laplace transform of this. We're just going to have to deal with this first part now. So here's where we are so far. We know we're going to be okay in that second term. Let's work on the first. The first term should have numerator omega, which is root 2/3. What it has is numerator 1/3. That's almost the same. If we just write 1/3 as 1 over root 2 times root 2/3, we could then introduce a root 2/3. So our first term, 1/3, I want root 2/3, so I've multiplied this by root 2, so I'm going to have to divide it by root 2 as well. Our second term, as we've mentioned, is already looking good. So with some work, you can double check our original expression of f of s is in fact equal to 1/9 times 1 over root 2 times omega over s minus a squared plus omega squared plus 2 times s minus a over s minus a squared plus omega squared. So here's capital F of s written in the two pieces that will be easy to deal with. Just for convenience, I'm going to go ahead and distribute that 1/9 out across the two terms. So we get 1/9 root 2 times the first ratio plus 2/9 times the second. Okay, so here is our function capital F, 1/9 root 2, and then this is omega over s minus a squared plus omega squared plus 2/9 times s minus a over s minus a squared plus omega squared. Through linearity of the Laplace transform and a table of Laplace transforms, here was the relevant couple of rows. Okay, we've got an omega over s minus a squared plus omega squared, s minus a squared plus omega squared, and this constant of 1/9 root 2 can factor out since the Laplace transform and therefore its inverse are both linear. Here we have s minus a over s minus a squared plus omega squared, which matches this in our table of Laplace transforms. And that factor of 2/9 is going to be factored out. So what do we end up with? 1/9 root 2 e to the at sine of omega t. There it is. And in the second term, this 2/9 has factored out e to the at cosine omega t. So here is a function, little f of t, whose Laplace transform would be the rational function we started with. And it may seem like an awful lot of work, but it's really just a bunch of basic algebra steps to make capital F of s look like things that fit the form in a table of Laplace transforms. It's much, much less work to do this basic algebra than to try to ask the question, can I magically come up with a function whose Laplace transform would be this. By guess and check or whatever, you would never think to start with this function here. Okay? So if the algebra of making a rational function, first you do partial fraction decomposition to get a bunch of individual terms, then you have to manipulate each of them to look like something that appears in a table of Laplace transforms. If that algebra is the scary part, that's something you need to address. It's basic algebra. You just have to be really good at it and do it quickly. But once you get to that point, it's just a matter of checking a table of Laplace transforms to go back and forth. So what have we discussed? Using tables of Laplace transforms, we can try to go backwards, find inverse Laplace transforms, a function whose Laplace transform is something specific. But we're not going to directly attempt to use the definition of Laplace transforms to somehow undo the process. That would be awful. Using clever algebra techniques and tables of known transforms, that's generally going to be enough. However, what we haven't addressed in this video or the previous is why we actually care about Laplace transforms and inverse Laplace transforms. We'll get to that next time.